Thank you everyone for joining us today. Technology Alberta every month has the opportunity to showcase tech companies that are using, local tech companies that are using AI to do great things. And it is definitely our pleasure to have Nanostics speak today on what they're doing. And then just a little background around Technology Alberta is that we're a volunteer organization that builds community and raises the profile of tech companies, and as well as the opportunities to work for these companies. So check out the Technology Alberta website. We have the First Jobs program, which really was co-founded by an AI professor, ways that, again, people can start on a part-time basis working with tech companies so that we can grow the tech sector across the province. So, and also the Aztec Awards is something that Technology Alberta is taking on this year. The event's November 4th. Nomination deadline September 15th, where we recognize outstanding work done by researchers, as well as companies in the tech space across the province. So please do nominate, self-nominate, or recommend others. Go to the Technology Alberta website. But without further ado, I am pleased to turn the floor over to Robert and to tell us more about Nanostics. Over to you, Robert.
Thanks a lot, Gail, for inviting me and for being able to do this talk here. So I'm very thankful to be here and probably switch things up for you guys. I'm assuming most of the talks you hear are going to be more academic focused about algorithms and things like that. So since I'm involved with Nanostics, which is a medical device manufacturer, I can give you probably a different perspective of what life is like doing data science as trying to deploy predictive models into the healthcare setting. So just a bit of background on Nanostics. We're a medical device and biotechnology company with a mission to provide clarity to people about their health and enabling better diagnosis and improving healthcare decisions. So we just try and use whatever technology we have at our disposal, and which can include AI, and improve healthcare in whichever way we can. That's really what we try to do. So we've been specializing in trying to analyze what's called extracellular vesicles within the realm of diagnostics. So extracellular vesicles are something that all cells give off. There's different types of, we call them EVs. There's different types of EVs. There can be really, really small exomeres that are under 50 nanometers. There's also pretty small exosomes that's close to 100 nanometers. There's microvesicles that bleb from the outside of the membrane that they're a bit bigger, can be up to a micron in size. And so basically the most important part is that all these EVs are essentially like blebs that come off from cells. And what's interesting about them is that on the outside of the EVs is a lot of the types of biomarker proteins and just whatever molecules that would naturally be present on the cell of origin. So one of the advantages of looking at these EVs instead of the cells of origin is that what happens if you're trying to find something like circulating tumor cells or local tumors that haven't even metastasized yet, you're not going to find a lot of them in the blood. But if you're looking at these really, really small particles, and each cell, potentially like a cancer cell, could give off hundreds to thousands of these, you can get a lot more of these smaller particles that are much easier to get inside the blood for us to detect. So, and if you're wondering how we came about with our name, we analyze nano-sized particles, and it's for diagnostics. So that's how Nanostics came about. So the technology platform that we specialize in is what we call microflow cytometry. It's not too important to go into the details, but I just think it's interesting how it works. So what we can have is any given patient sample that's a fluid, such as blood, urine, even saliva, whatever. All these different types of fluids are going to have these EVs inside of them. So we want to be able to characterize what these EVs are. So what we can do is have fluorescent probes, and our probes could be antibodies that could bind to specific proteins of interest, or anything else that just binds to what we want it to bind to. And when we have fluorescent tags to them, that allows these EVs to show up with fluorescence when we analyze it with our microflow cytometer shown on the bottom right. So when the incubated sample that has our probes on it, the sample itself will go through a really, really thin sheath of fluid. And then we can hit all of these particles, these EVs, that go through this stream with a bunch of lasers, a series of lasers. And if the particles are big enough, they'll scatter the light enough, detected by some of these light detectors. And then that's what triggers detection of events on the machine. And not only are we looking at how much light scatter there is to roughly approximate particle size, based on the relative amount of fluorescence that's on each of these individual particles, we can also get a relative quantification of the different biomarkers of interest. So we wanted to use this technology in healthcare, and we decided to focus first on prostate cancer. So our CEO, Dr. John Lewis, he at the time was the chair of prostate cancer research at the University of Alberta, and put together the Alberta Prostate Cancer Research Initiative, or APCARI. So APCARI is about putting together the scientists and clinicians all collaborating together in the hopes of trying to promote prostate cancer research, both at the basic science as well as the clinical level. So through APCARI, we had access to a bunch of clinical samples that were going to a biorepository for us to develop tests, which made this a really good first cancer to go after. So just to give a little bit of background information about prostate cancer, it's diagnosed specifically with biopsies. Prostate cancer is never diagnosed with a blood test. There's PSA tests to determine who would be at higher risk for prostate cancer, but it needs to be followed up with a biopsy. So biopsies typically involve a ultrasound probe that can go through the rectum, and then it can push needles through the rectal wall into the prostate itself. And typically there's about 12 cores that are taken from a biopsy itself. And then once you get all these biopsy tissues, they get stained and a pathologist will look at it. What the pathologist is looking at under the microscope is going to be for any cancer cells, but on top of that, if it sees any type of cancer cells, what's the morphology of those cancer cells? If it looks like the cancer cells look fairly normal still with small glands, it's just a bit abnormal, it's going to be classified as a grade group 1 prostate cancer. And grade group 1 prostate cancer is the least aggressive. Some people consider it a benign disease, and that many people will die with this disease, not of it. But as the cancer cells look more and more dysregulated and less glandular, it gets higher and higher grades. And if you get all the way to grade group 5, this is a very aggressive disease where many people will end up having metastatic disease and unfortunately will pass away more quickly with it. So some of the issues currently with prostate cancer is that the biopsies themselves are quite painful. Any man that's had one typically does not want to have one unless highly recommended by their doctor. And because they're pushing the needles through the rectal wall, and there's a lot of microbes in the rectum, there's also the chance of sepsis, which can be quite life-threatening, between 1% and 2% chance of it. And this is very, of course, not good at all. So we want to minimize the amount of unnecessary biopsies. Unfortunately, because of the PSA screening that we do, PSA is being prostate-specific antigen tests, it can be quite sensitive when we look at everyone, say, above 3 nanograms per milliliter going for biopsy. But unfortunately, it's not very specific. And depending on what healthcare system you're in, up to 80% of biopsies might even come back as negative. And if you have this many people who are undergoing these painful and potentially serious complications involved with biopsies, it's a lot of a waste of money, and it could be a health hazard as well to the patients. In addition to that, there's also the concern of overdiagnosis of prostate cancer, since a lot of men, when they get told they have grade group 1 prostate cancer, they hear the C word, cancer, and they immediately think, I need treatment, this is going to kill me. That's just the natural reaction. But because it's such a benign disease in most cases, it turns out that many people that have grade group 1 cancer don't actually need treatment. But as soon as you tell them they have grade group 1 cancer because they have the biopsy, many men just go for treatment, and it may be unnecessary. So it's extra costs and complications from the treatments as well. So the goal is to try and figure out who would have grade group 2 and above prostate cancer. We want a blood test that can figure this out as best as we can. And this is just a curve that shows the probability of a cancer coming back after it's been treated with surgery to cut out the prostate, suggesting that with these higher grade group cancers, even if you cut out the prostate, given enough time, it's very likely that this is going to come back, suggesting that it was already metastatic even before surgical treatment. But with grade group 1 cancer, it's a lot less likely that's going to happen. And this is just if the cancer comes back, if progression happens. It's still going to take years after this before it becomes a fatal disease. So it's a relatively slow-growing cancer. So our goal then was to try and develop a microflow cytometry assay specifically for grade group 2 and above prostate cancer, using probes that would be for prostate specific, as well as that's specific for aggressive cancer biomarkers. So before I get into any of the other, the clinical study itself or the results, it's important to have an idea of how well could this test possibly work. It's always easy to say, oh, you should be able to have perfect accuracy, but that's not actually the case specifically for prostate cancer, because the biopsies themselves are imperfect. The biopsy needles could miss the tumor or could miss the regions of the tumor that have the more aggressive cancer cells, so that we can't properly classify what the grade was. And on top of that, the pathologists themselves don't always agree even when looking at the exact same slides of what the grade should be. And the Cohen kappa depending on the study you look at, can range from 0.43 to 0.74, which is a pretty big range. So to try and get an idea of what is the maximum AUC our test could possibly be, we looked at a study that had from 2012 from Johns Hopkins University that had over 7,600 results of biopsy as well as surgical pathology. So surgical pathology is going to be similar to biopsy in that a pathologist will look at it and determine the grade of the cancer. But the difference with surgical pathology is instead of getting biopsy needles, which can miss the tumor, this specimen is typically collected after surgical treatment of prostate cancer, where they cut out the entire prostate so that the pathologist has the entire prostate to look at to find whatever they can find. So surgical pathology is the best ground source truth that we have of what the grade group is. So the question I asked was, if we had a test that in theory knew exactly what the surgical pathology was, but we use it to try and predict what the biopsy grade group is, because most of these blood tests that are for prostate cancer don't predict surgical pathology, they predict biopsy, since biopsies, the diagnostic treatment, or diagnostic, not treatment, but test itself, sorry. So as it turns out, when taking the data that looked at probabilities of if you have a certain surgical grade of prostate cancer, what would be the biopsy grades, we can make simulated cohorts and try and figure out what the maximum AUC could possibly be. And it turns out it's about 0.82. So we knew that that was the benchmark. That's the perfect test. You can't really do better than that. So going on to the clinical protocol itself, we were recruiting men between the ages of 40 and 75 years of age. They had to have a PSA of 3 nanograms per milliliter or greater. And we knew they needed to get referred so that we'd have referred for a biopsy, since we could then figure out how well the test worked for predicting the grade group on biopsy. So we had 3 main clinical sites for this study. We had the Kipnis Urology Clinic here in Edmonton. We had Johns Hopkins University in Baltimore. And we also had the Prostate Cancer Center recruiting for us in Calgary. So when we did the training of the models as well as evaluation, we used the Kipnis and Johns Hopkins University data in the training cohort. And then we wanted to make sure our validation set was a completely different clinic. So we chose Calgary's data at Prostate Cancer Center. So we're at these 3 different recruitment sites. We found men that want to take part in the study. They signed consent forms. We were able to collect blood from them so that we could rerun PSA as well as free PSA. They filled out some surveys talking about their health history. And then when we had all that information, we could transport the blood samples to Dynalife here in Edmonton, where we were running our test with our microflow cytometer. And then eventually when the men got their biopsies, we could then figure out how well was our test working. Most importantly on that, once we locked down the algorithm, how well was it working on the validation data from Calgary? And we also wanted to compare how well this algorithm was working to that of other risk calculators that tried to predict grade group 2 and above prostate cancer. There's the ERS-PC risk calculator 3, which is a European risk calculator. That's probably the best, most equivalent risk calculator I could find in a pre-imaging setting before you know things like prostate volume and before you get MRI data. There's the PCP-TRC calculator. That's probably the most well-known risk calculator, but it was made quite a while ago, a few decades back. And it was originally made so that it didn't have free PSA, but it also could include free PSA, which is one of the other features we were using. And then there was the more contemporary North American risk calculator, PBCG. It's considered should be replacing PCP-TRC, but it does not have free PSA. So we have a variety of different data here. We have the data that we generate from our microflow cytometer. And then we also have the data from the clinic itself, PSA, free PSA, the patient age, whether or not their digital rectal exam was normal or abnormal. Typically, abnormal means there's some type of asymmetry. And whether or not they've had previous negative biopsies. Those were our main clinical features that we found to be most useful. So after trying out a bunch of different ways of making predictive models, it turned out that the best way to analyze this data was to treat the data set separately. Since we had a lot of features from our microflow cytometry and a lot less features for the clinical data, but the clinical data was some of the most important. So we didn't want to dilute some weak features over to that model, the clinical model itself. So we had our own algorithms that could analyze the microflow cytometry data in terms of which particles were positive or negative for our biomarkers, what were the concentration of different types of particles we found, also looking at different particle phenotypes based on particle size. And then from all those features, we could come up with what we call the flow score. We would take those features, use machine learning, get a single probability of what grade group 2 prostate cancer would be from just the microflow cytometry data. We would do similar types of machine learning on just the clinical data to make a clinical score, and then do a second layer machine learning with a simplistic logistic regression model to get the final risk score of what was the probability of what we say here, clinically significant prostate cancer, which is grade group 2 and above. So here's the overview of how well the different individual features as well as the risk calculators worked in the validation data from Calgary data. So when we look at individual features, like previous negative biopsy, the AUC is actually quite small, 0.53, but it is significantly different between those people with grade group 1 prostate cancer as well as a negative biopsy versus people with grade group 2 prostate cancer and greater. When we look at the digital rectal exam, it seems to be more valuable with AUC of 0.62. Age is useful, 0.65 AUC, and PSA is also quite useful, not surprisingly at 0.65. More interestingly, free PSA by itself, and I should say free PSA just means the PSA that's not bound to anything, it's just free floating, whereas the other PSA here is total PSA, whether it's bound or not. So free PSA by itself wasn't actually very useful at 0.53 AUC. But if you look at the ratio of how much of your total PSA is actually free, that turns out to be the most useful single feature out of everything we looked at 0.71. And then when we look at some of the other risk calculators, like the PCP-TRC, it uses very similar features to what we used here, but it also added in some extra things like family history, as well as race. We didn't include that because in the Alberta data sets, those features just never added value. The PCP-TRC had a 0.77 AUC, which was not bad. It's pretty close to what we find from other clinical studies as well. The European risk calculator wasn't actually very good at 0.71. So then we get into what we were doing. Our flow data, we knew it wasn't going to be as good as the clinical data itself, but we were a little surprised. It was less than we were expecting from preliminary results. It was 0.55. And then what also surprised us was that the clinical data just by itself with these features was actually very high at 0.80. And we're getting pretty close to that theoretical maximum of 0.82 without even needing any of this microflow cytometry, because when you add the microflow cytometry, it doesn't even improve things, unfortunately. So on the one hand, it was disappointing to see these results, but on the other hand, I think was also a better opportunity to come up with something that would be more clinically useful. Since if we try and make a test that doesn't have any of the complicated microflow cytometry aspects to it, and we just focus on making the most out of the information we have from PSA, free PSA, and just questionnaire information, it'll be a lot cheaper this way. So the throughput, when we look at the microflow cytometry test, we can look at about 90 samples in an 8-hour shift on one machine. The Roche Cobas 8000 system we use to run PSA, free PSA, and DynaLife, it can run up to 8,000 samples per hour. So because it's so much higher throughput, there's significant cost savings. Each PSA and free PSA, depending on your economies of scale when you buy the kits, they could be under $20 each. And the amount that HS could typically spend on a flow cytometry test is hundreds of dollars. It's a lot more expensive. So, and it's also really important to realize that the Canadian Urological Association guidelines for this year, when they talk about other types of blood prostate cancer tests, like the 4K score, Phi test, PCA3, they acknowledge that these other tests can increase or improve our prediction of clinically significant prostate cancer, but that the tests themselves are quite expensive. They're not publicly funded. And at the present, they're not even recommended for these other tests to be used. And some of these other tests themselves can cost hundreds of dollars as well. So if we stick with having to force the use of this microflow cytometry with ClarityDX Prostate, we're going to be in the same boat as everyone else. The test is it's probably not going to be used or recommended for use in Canada. But if we can keep it really, really cheap, there's a chance this could help a lot of people. So that's our goal. Try to create a model using relatively inexpensive to acquire clinical data. So we wanted to then figure out, okay, we have this clinical data. How can we make this the best possible model? And so these were the 5 main features we found useful. We tried out a bunch of different machine learning algorithms. And for each of these algorithms, I was doing pretty heavy grid searching for which hyperparameters gave the best results in the training data before then evaluating it on the test or validation data set. So what was quite interesting is that the powerful nonlinear models like XGBoost, they performed extremely well on the Edmonton and JHU data sets. But as soon as you go to the other clinical site at Calgary, they actually don't perform that well. And the best algorithm turns out to be simple logistic regression. So this is a really important point in that it shows evidence that there's going to be a lot of variability in the clinical data between sites. And when you have this type of variability, this can really limit on what type of models you can use. We then want to see of the clinical features that seem to be useful. What happens when you get rid of any of them? Does this decrease performance? Is there any feature we can get rid of to just simplify the test? And removing any single one of these features significantly decreased the performance in either the training or the validation data set using DeLong's method. And probably what's also really interesting to point out here is that free PSA ratio is the most important feature in the model. And this is the one feature that doctors don't have in Alberta. We have access to all these other things, but in Alberta, we don't run free PSA. So I'm also hoping that this research could help make clinicians realize the value in free PSA tests and make it more of the standard of care in our province. So for IP reasons, I can't go into full detail of how we do some feature transformation and feature engineering, but I think it's just in general, I can say that because we're limited to using something as simplistic as a linear model like logistic regression, we need to make sure that we change our features so that they better correlate with, so that changes in features better correlate with changes in the risk of the positive class, in this case, grade group 2 and above prostate cancer. Because that's the way logistic regression is going to work. Any X unit of change in that feature is going to change your log odds of risk of the positive class, essentially, without any change in that risk, no matter what your values are. So by doing some digging into looking at how the risk changes for each feature and then changing your features themselves, we were able to slightly improve the performance of the test from 0.808 to 0.812 for both the training and test data sets. So this is the current performance of the test, and it's actually pretty close to 0.82, which is as good as we expect this could be. Using the engineered features, again, we see we outperform pretty much every risk calculator I've ever tested when looking at AUC, and as well as when looking at sensitivity and specificity pairs for both the training cohort as well as the validation cohort. And because it performs very, very consistently across clinical sites, it's good evidence that it should also perform pretty well in other clinical centers as well. So where we're trying to position the test itself would be after a first elevated PSA. So in Alberta and in many places around the world, before someone gets a biopsy, typically there's going to be 2 PSAs. So the first PSA, if it's elevated, is typically an indication that something might be off, but sometimes people have an elevated PSA because maybe there's inflammation in their prostate. So there's typically a second PSA that's going to be ordered. And what we'd like to do is, instead of just ordering nothing but a second PSA, you'd order Clarity DX Prostate, and we would rerun PSA like normal, but we're also going to run free PSA. So that would be the only extra additional cost in Alberta, would be running that extra free PSA. And with other free to acquire information about the patients, those other 3 clinical features, we could then come up with that risk score for our test. So if they're in the high risk group, based on that threshold that gave us the sensitivity of near 95%, if you're in that positive group, being high risk, you would then be recommended to go on for subsequent procedures like MRIs or biopsy. But if you're in the low risk group, we can just continue monitoring, and it would make sense potentially to not go to the biopsy at this point. So we still have to do health economic studies to determine how much cost savings there'll be exactly and how this affect healthcare systems, but we're in the process of doing this now. So now that we have a general idea of what it is we want to do, there's going to be a whole bunch of questions. So, and many of these types of questions need to be answered by pretty much every medical device manufacturer, or many of these questions at least. So how is the test ordered? Does the doctor have a piece of paper where they just check off your test? And typically that only happens when the healthcare system approves of your test, and then and only then will that become a possibility. So we're not at that stage yet. We're still looking for Health Canada and FDA approval, but we're hoping to eventually get at that stage. How are you going to collect your input features? Are you going to have a requisition form where they start answering certain questions? Is there going to be a web app that does this? If you need to run any type of blood tests, how are you going to get the blood samples, transport them? Who's going to be running these blood tests? In our case, running PSA, free PSA. Is it going to be Dynalife? Do we want to become, as Nanostics, an accredited lab, which may have some business advantages by doing this, but adds extra work? So these are important logistical questions. Where does model inference take place? Is it going to happen on a computer that's local within the lab? Is it going to be happening in the cloud? And if you do in the cloud, in some instances, there may be some greater risks for cybersecurity, but there's also a lot of advantages in terms of being able to deploy this in many different places and being able to store all the results in databases that grow as big as you need them to, which solves a lot of problems as well. How does the ordering physician get the results back? These are important questions as well. And what takes up most of my time isn't actually the data science. All that data science stuff, that's the easy part. It's complying with regulatory requirements as a medical device manufacturer. So I just want to briefly go over some of the things that we need to do in order to comply with regulations. So if you want to be a medical device manufacturer, you have to develop and operate under a quality management system. So there's an ISO standard for this, 13485, and this is international. So this isn't all the points that's in this standard. I don't want to go through all of them. That would be very tedious and boring. But in general, some of the higher things you need to think about is how do you control your documents and your records? If you have a new document, how do you do this? Who approves of your documents? Do you have an audit trail of when documents were made, when documents were edited and changed? You need to be mindful of all your different resources and have procedures on this in terms of human resources, the infrastructure you're working with, your work environments. The biggest part would probably be of this standard is product realization. What are the requirements of your medical device? What does it need to do for the users, for user requirements? When you're doing the design and development, what are your design inputs, design outputs in terms of specifications? How do you verify that you've met your specifications? How do you validate that the device itself actually met your user requirements? What's your plans for making sure that you can transfer this into the real world? And what are your plans and how are you going to execute maintenance on the medical device if something goes wrong, if something needs to change? So all of these activities require their own documents and procedures. There's purchasing aspects in terms of how you qualify your suppliers. If you get products from anyone, how do you verify that the product is appropriate, which may be kits for blood tests? And you also need to make sure that you control your production environments and all services that you get. If you have to install software, what's your procedures on how you install software? Or installing pretty much anything, to be honest. How do you do monitoring? If someone gives you feedback, do you just throw that away because you just don't want to deal with it? Is that going to be a serious problem? If someone gives you a complaint, how do you handle that? You need a procedure on it. If something goes wrong, when do you report this to the authorities? And how are you going to do the reporting? These are their own documents. How do you do internal auditing? And if there's some type of problem that happens, like a non-conformance, what do you do in that situation to handle the problem? So there's a lot of things you have to think about, a lot of documents you have to write. And that's just for the one standard for your quality management system. Then there's standards for risk management. When you do risk management, how do you assess risks? How do you design risk controls to deal with these risks that come up? Risks might be someone foreseeably using your software wrong, interpreting things incorrectly. A risk could be cybersecurity, it can be a lot of different things. And you also need to do verification that your risk controls work correctly and that they become requirements inside of your product itself. So it's actually a lot to think about and document. And since we're talking about predictive models, this is clearly going to involve software. So software itself has its own standard for basically the lifecycle development of software in medical devices. That's IEC 62304. The stuff at the very top, this is pretty similar to the previous quality management system standard about customer needs, just like user needs and how you develop the system. So the software development is kind of lower level than this. When you're about to develop software, what's your plans for how you develop software? This can include things like the version control systems you're using, the libraries you want to use, a whole bunch of other things as well about how the process is going to be for software development. What are the software requirements that you need? These are typically higher level, and you may put this into some of the design inputs for your medical device itself, but ultimately you do have to come up with them. If your medical device is a higher class and higher risk, you may have to come up with architectural diagrams and detailed design information, which can include things like describing the entirety of what are all the different classes you have of your software, what are the different methods, functions, what's the parameters, default values, and it all needs to be written out. It's quite a bit of work. And then there's the aspect of testing your software, unit testing, integration testing. This is more so to make sure that what you said in your detailed design and architectural diagram works as intended. And then when you get to system testing, this is more so about making sure you verify that your user or software requirements here technically would be in a document called the software requirement specification, making sure that you verified that you did everything you said you do there. The software has the input fields they need to have, the user can do these functions with your software, etc. It's a bit higher level system testing. And when you do all that, you can then validate your software, which doesn't validate the medical device, just the software that's in your medical device that you're currently developing, since these requirements aren't necessarily things like the clinical performance. It's not quite that level. On top of that, this software standard deals with things like how do you manage the configurations of your software if you change libraries, versions, or what have you. And what happens if you have defects in your software? How do you handle it? How do you track it? Many of these are their own documents, SOPs, and it's a lot of work. So on top of these things, there's other guidance documents the FDA has about medical devices that involve a lot of things software. I'm only going to point out at this point things like cybersecurity, since I haven't talked too much about it. Cybersecurity, of course, is a big issue. You need to make sure that you take security seriously inside of your company, making sure that you have appropriate administrative controls, SOPs, dealing with how you're going to minimize the risk of cybersecurity events and how you're going to deal with it if it happens, as well as how do you come up with physical safeguards, technical safeguards for your company, for your products, etc. There's also going to be, if you're a medical device manufacturer, if you're for profit, you're probably going to want to really think about intellectual property. What are you doing that's unique? How do you make sure you can protect your company by filing some type of IP? And I talked a bit about it previously, but you'll also want to do health economic studies. Just because you have a model and you know what the AUC or sensitivity or specificity is of your model, that's typically not enough information for hospitals to decide if they want to use your model, because they don't know exactly how this is going to affect them in terms of how much is this going to change their costs. If you start having more tests, this might increase their costs, but it might improve patient outcomes, or maybe these tests decrease further procedures, which might decrease costs. They don't really, it's really hard to do this unless you do some serious modeling. So those are other clinical studies that need to be done. So the reality is, if you want to become a medical device manufacturer, to do all these activities, you're going to have to raise millions of dollars essentially, and have a strong team that's specialized in a variety of different areas, whether it's software development, quality, regulatory, etc. And when you don't have expertise somewhere, which is likely going to be the case, you have to find trustworthy consultants that's going to give you the advice and information you're lacking. And ultimately, coming up with all those different procedures, SOPs, processes, it's going to take years worth of work. We've been working at this for 5 years now. We've made a lot of progress on hundreds of documents and a pretty solid quality management system. But to this day, we still work on it. And as some of our consultants have told us, it's a never-ending process, even for the companies that have been around for decades, as you're just trying to improve everything you're doing. So looking back at some of the work that we've been doing with Clarity DX Prostate specifically, I think the most important lesson for me was just how much bias there is in the data between different clinical sites. The fact that we had to resort to using a logistic regression, because if we try to use anything more powerful than that for finding nonlinear patterns, it just overfit to a specific clinical site. It really showcases that you really have to get a lot of data. And some of these biases that can happen might be because different clinics might use different medical instruments. They might have different kits for the medical instruments or use different software potentially. All of these things can affect the type of raw data that you get. And sometimes it can be really subtle things, such as there might be difference in procedures between clinics. If when doctors do a digital rectal exam, this test is not standardized in how they're trained. They're not told exactly how much pressure to use in their finger and where to put their finger and how to classify an abnormal versus normal. And different clinicians may come up with a different result with that test. Pathologists and radiologists, they're going to be trained differently. When they look at their training data and try to figure out what it is they should be looking for, their eyes might be looking at different regions, and then their brains might be thinking that slightly different patterns are important. And ultimately, it leads to different results, different labels. And even some really simple things like if you're looking at imaging data, which is not an issue for our specific case, but I've heard of this before, where different clinics might have different ways of loading patients inside of the imagers. Maybe some clinics put a pillow underneath their back. Maybe some clinics don't have that. So what type of biases might there be between different sites because of these differences in procedures? So my general feeling is that if you want to use advanced AI, like the types of algorithms everyone here likes to develop and work on, you have to have a very big and diverse data set. Otherwise, you're just better off using logistic regression. And this is a really, really important point, since in the priority, I knew most of the work we do at academia is just trying to come up with more efficient algorithms. But at least specifically in healthcare, that's not even the top priority, because you can't use those big algorithms unless you have a data set that allows for them to make it worthwhile. So there are some data, of course, in the literature where these advanced AI algorithms do work quite well. There was a wonderful study, I believe last year, in Nature Protocols by DeepMind and Google that looked at creating a variety of different machine learning models in healthcare, and they looked at a bunch of different tasks. In this case, I'm just showing mortality in admission within 24 hours or 48 hours. And they were using data from the US Department of Veterans Affairs, which is over 700,000 patient data from over 1,000 different sites, which is amazing data set. And even then, it was still in some ways biased because it was the Veteran Affairs, so the vast majority of these subjects were male. But regardless, we can see from this that the advanced neural networks here, the recurrent neural networks, significantly outperformed that of XGBoost, which significantly outperformed that of logistic regression, which is the typical pecking order we would have expected in terms of how powerful these models could be. So we can use this amazing AI algorithms, but we first have to figure out how to get the data sets. So in Alberta, there is the ability to have, there is a lot of data that's being centralized with ConnectCare through Alberta Health Services. ConnectCare right now is prospectively collecting and centralizing all of their diagnostic images, all their lab test results. It's all going in ConnectCare. And this is servicing over 4 million people in Alberta, which is building a remarkable clinical data set. So being able to do machine learning on the data in ConnectCare would greatly improve our ability to make accurate and reliable predictive models. But unfortunately, accessing ConnectCare is extremely difficult because you pretty much need to be inside AHS to have any hope of touching that data. This is basically what, from our talks with them, what's been happening. In another project with AHS, we've had to come to the agreement that we will hire someone within AHS to do the work we want to do to get access to this data, just so that we could analyze it. And that person essentially would become an AHS employee and not our employee. So that's how hard it is to gain access to a data set like that. So what are some of the ways we can try and get around some of these privacy concerns? Because that's the main reason they don't want anyone to have this data is because of privacy. There's a lot of talking about using synthetic data, which is an interesting approach. It would allow researchers to analyze the data any which way they'd want to, and it may not contain any type of the original data, and I stress the may there, but there are some concerns with this as well. If you have a low fidelity synthetic data set that doesn't match the real data very well, you could end up having models that just don't perform very well, which isn't good for anyone. And if you have really high fidelity synthetic data that matches your training data really well, there may be more privacy concerns where what happens if this model can completely replicate the data that was used to make it. This could be a data breach, and data breaches are not good for anyone. And on top of all of this, even if you can get around the issue of fidelity and privacy, the FDA will never, ever approve a model that was made, but that was evaluated by fake data. You're always going to need real data to figure out how well this works in the real world. So this doesn't completely solve the problem of we need real world data. So I've been thinking about this quite a bit about what would be the best way to try and deal and tackle what I believe is the biggest issue in AI in healthcare. And I think it should be possible to come up with a framework where we separate what happens for the researchers come up with instructions of how they want data to be analyzed. They give the instructions to people who own the healthcare data, and they can use those instructions to directly run them on a framework that knows how to run the data. So quickly, what could happen is that if you have a specific framework here of that health data owners could use some software and say, here's my data set. And then the software could look at whether it's a database, look at what all the database fields are, and basically return a data dictionary of what is in the data. It's not the raw data, it's just like column names. You could think of it like that. And then the data dictionary can then just be sent to the researcher. Then you can have some software that can basically say, okay, figure out how do I want to do training, validation, which people go in training, which people go in validation, which column names do I use as features, which column name do I use as a prediction target. And then when you add all the instructions together, you could potentially encode it inside of a JSON file to make this RESTful. So it's fairly easy if anyone else wants to make some other software, as long as they know the specifications of how to make the instructions, they could do so with different software as well. The JSON file with instructions can then be given back to the data owners, which can then just execute the instructions directly on the framework itself, if the framework itself knows how to build all the models based on the instructions. At that point, you could make sure that the models that are made are only the models that do not have the original training data in it. So no k-nearest neighbors models, only models that you could trust. And the aggregate statistics of the models themselves in terms of AUC, sensitivity, specificity pairs, as well as the models themselves could be potentially given back to the researcher. There may be some privacy concerns if you make a really huge neural network that memorizes the training data set, and there may be some work that needs to go on there to minimize the risk of that. But I think in theory, with enough work, it's something that should be possible. So the advantages of such a system would be that data privacy is intact. The researchers never get a copy of the data. They never see the data, which is even better than getting de-identified data. It's safer. You can train and evaluate the models on real healthcare data, not fake stuff. You don't have to worry about low fidelity. Some of the downsides might be, it might be harder to understand the data itself if you can't see it. You potentially could add instructions here that could do aggregate statistics on it, such as making histograms, things like that, but it would have to be extra functionality to try to understand it. And if you wanted to clean the data, if you can't see the raw data, it might be a little bit harder. So there might be extra functionality there needed to do such things. But this is something I really would like to help develop. And if there's other people, PIs, that would like to collaborate, either intellectually or even with software development, I'm all for such collaborations. So I'll wrap up there. A lot of people to thank for the projects and the work we've been doing, the whole team at Nanostics, with John Lewis as our CEO, people at Apkari that helped build the clinical database for our Apkari 05 study, which was about developing Clarity DX Prostate, people at Dynalife, CEO Jason Pincock for all his helpful advice, as well as Brenda and Brad, our go-to people when we need help. Our clinicians for getting people, for recruiting people for our clinical studies and helping the design of our studies, as well as some individuals, Russ Greiner, as well as Ross Mitchell, for discussions on all things machine learning.